Welcome to MathAlgo Studio, where math meets code. This is Computational Geometry series, designed to take you from beginner to advanced. You will see more than 200 plus videos on this series. Imagine you are working in CAD software or a simulation engine. How does the software know whether two edges are perpendicular? And how does it compute the direction of a surface normals in 3D space? The answer lies into powerful vector operations, dot product and cross product. In this lecture, you will understand dot product and cross product geometrically, not just as formulas. By the end of this video, you will also see how to implement them in C++ and understand where exactly they are used in computational geometry. Now let's begin lecture 3, where we move into one of the most important building blocks of computational geometry, vectors. First, let's understand what a vector actually represents. If we have 2 points in space, point A and point B, then the vector from A to B is written as a. Mathematically, this vector is obtained by subtracting the coordinates of point A from point B. So we write vector AB equals B minus A. Geometrically, this vector represents both the direction from A to B and the distance between them. Now, depending on the dimension we are working in, vectors are represented differently. In two-dimensional space, a vector is written as an ordered pair x, y. In three-dimensional space, a vector is written as x, y, z. These components tell us how much the vector moves along the x, y, and z directions respectively. Next, let's talk about the magnitude of a vector, which simply means its length. Suppose vector AB has components x, y, z. Then the magnitude of this vector is calculated using the distance formula. The magnitude of AB is equal to the square root of x squared plus y squared plus z squared. This formula comes directly from the Pythagorean theorem extended into 3 dimensions. Let's take an simple example as point A is 2, 2, 4. And point B is 3, 4, 6. Then vector from A to B is equals to B minus A. Finally, vector AB is 1, 2, 2. And magnitude of vector AB is equal to the square root of 1 squared plus 2 squared plus 2 squared, which is squared root of 9. Finally, we get length of AB is equals to 3. Understanding vector representation and magnitude is extremely important because these concepts form the foundation for dot products, cross products, projections, angles between vectors, and almost every 3D geometry algorithm we'll see later. In the next part of this lecture, we'll build on this and explore dot product and cross product along with their geometric and computational significance. Now let's move to the dot product, which is one of the most important operations on vectors. First, let's understand the geometric meaning of the dot product. The dot product essentially measures how much two vectors are aligned with each other. Here, we have two vectors, vector A and vector B, and the angle between them is theta. If we project vector B onto vector A, the length of that projection is considered here is x. x is equals to magnitude of b into cos theta. So geometrically, the dot product tells us how much of vector b lies in the direction of vector a. This is why we say the dot product measures alignment between vectors. Now let's write the mathematical definition. The dot product of two vectors a dot b is defined as magnitude of a times magnitude of b times cos theta. This formula directly connects geometry with algebra. In practice, especially in programming, we usually compute the dot product using the coordinate form. If vector A has components ax, ay, az, and vector B has components bx, by, bz, then the dot product is calculated as ax times bx plus ay times by plus az times bz. This coordinate form is extremely efficient and is what we use in C++ implementations. Dot products are widely used to compute angles between vectors, check perpendicularity, perform projections, and solve many real-world problems in graphics, physics, CAD, and simulation. Now let's see how we can implement the dot product in C++. First, we define a simple vector 3D structure. This structure stores the three components of a vector x, y, and z. We also use a constructor so that we can easily initialize a vector with given values. Next, we define a function called dot product. This function takes two 3D vectors as input and returns a double value. Inside this function, we directly apply the mathematical formula of dot product. We multiply the corresponding components of both vectors, x with x, y with y, and z with z, and then add them together. So mathematically, this is A dot b equals ax times bx plus ay times by plus az times bz. Now, inside the main function, we create two vectors, vector a with components 1, 1, 3, and b with components 2, 4, 6. Finally, we call the dot product function, pass vectors a and b, and print the result on the screen, that is 24 here. Now let's look at some special and very important cases of the dot product. These cases help us quickly understand the relationship between two vectors just by looking at their dot product value. First case. If two vectors are pointing in the same direction. Here, the angle between them is 0 degrees. Since cos 0 is equal to 1, the dot product AB becomes magnitude of A times magnitude of B, which is the maximum possible value. So when vectors are aligned in the same direction, the dot product is positive also. Now move to second case. If the two vectors are perpendicular to each other. In this case, the angle between them is 90 degrees. And we know that cos 90 degrees is 0. That means the dot product becomes 0. This gives us a very powerful test. If the dot product of two vectors is 0, then the vectors are perpendicular. This idea is heavily used in geometry, graphics, and collision detection. If the vectors point in opposite directions. Here, the angle between them is 180 degrees. Since cos 180 degrees is minus 1, the dot product becomes negative. So when vectors point in opposite directions, the dot product is negative, indicating opposite alignment. To summarize these cases, positive dot product means vectors point roughly in the same direction. Zero dot product means vectors are perpendicular. Negative dot product means vectors point in opposite directions. Understanding these cases allows us to quickly analyze vector behavior without complex calculations. We'll use this intuition when solving problems and writing C++ code for vector operations. Now let's understand the important properties of the dot product. First, the dot product is commutative. This means the order of vectors does not matter. Vector A dot B is equal to B dot A, and mathematically it is written as a dot B equals AB cos theta. Second, if the dot product of two vectors is 0, then one of two things must be true. Either one of the vectors is a zero vector, or the two vectors are perpendicular to each other. This property is very useful when checking orthogonality. Third, when we take the dot product of a vector with itself, we get the square of the magnitude of that vector. So, our dot A is equal to the magnitude of a squared. Finally, the dot product follows the distributive law. That means if vector A is dotted with the sum of two vectors B and C, it is the same as A dot B plus A dot C. These properties make the dot product extremely powerful in geometry, physics, and computational applications.